The role of autonomous robotics in agriculture is maturing, and both research and industry are part of this process. Collaboration between the two requires objective benchmarks to assess the performance of robotic systems. Autonomous robots, besides dealing with the most tedious and wearing tasks, enable new and green ways to perform agricultural operations, greatly reducing and optimizing the use of resources such as water, fertilizers, and pesticides. The Metrics project organizes challenge-led robotics competitions in 4 areas: healthcare, inspection and maintenance, agri-food, and agile production. ACRA is a European Union-supported benchmarking competition where robots are tested in real-world agricultural activities and robot performance is evaluated according to rigorous scientific criteria to provide objective and repeatable results. The Romi rover successfully participated in both the ACRA Dry Run in September 2021 and the first ACRA Challenge in June 2022. It was seen as an important step in completing the European Union Romi project to quantitatively measure progress over time and to be able to use the ACRA results as well-defined technical specifications to certify the performance of the rover. The ACRA Challenge comprises 5 functionality benchmarks and 2 task benchmarks. The minimum entry requirements for any robot was the ability to complete at least 2 functionality benchmarks and 1 task benchmark. No team was able to complete the leaf area or biomass estimation challenges, and the Romi rover was the only robot to be able to participate in all of the remaining 5 benchmarks. A proud moment for the Romi team. Competitors in the ACRA Challenge arrived from different sectors of research, some sponsored by industry, and others sponsored by research grants in the same way as the Romi project is sponsored. Throughout the development cycle of the rover, a number of changes were made during iterations to improve the performance of specific aspects of the rover. Both the navigation and plant discrimination algorithm were enhanced above and beyond the original proposal. Using this enhanced functionality, the rover was the only robot to participate in 5 benchmark tasks rather than the 3 required as a minimum. The rover participated in plant discrimination, weed destruction, field navigation, intra-row weeding, and crop mapping. The goal of the plant discrimination task is to test the robot's ability to detect which plants of a row are weeds and which are crops. Performance metrics compare plant classification produced by the robot with the ground truth or reference labelled images. The initial proposed plant discrimination deliverable for the Romi project was based on plant size, and whilst this went well, the plant detection algorithm has since been greatly enhanced. The Romi rover is now able to detect not only plant size, but also plant type, based on this more advanced machine learning algorithm. The goal of the weed destruction task is to destroy, in intra-row, the unwanted plants or weeds whilst not damaging the crop. Crops and weeds in a fixed size area are counted both before and after the weeding action, and an assessment is made of the weed destruction effectiveness. During the task, the organisers of the ACRA Challenge made available a number of coloured tags to help contestants distinguish between the crops and the weeds. The Romi rover, however, was able to participate and distinguish itself in the challenge using its plant recognition algorithm and training, rather than the coloured tags. The use of a mechanical hoe allows the Romi rover to be very precise in its weeding, accurately detecting the crops and actively destroying everything else. Whilst the Romi rover may not be one of the fastest machines in development, it is highly accurate and performed well in the weed destruction task. The goal of the field navigation task is to navigate through planted field rows without causing damage to crops. Performance metrics consider the amount of damage caused by the robot to the crops and the time to complete the task, as well as the accuracy of the robot as it traverses a number of non-linear rows. Initially, the rover was designed to follow physical rails for navigation. Whilst this system worked well, it involved the installation, displacement and removal of the rail system, incurring additional cost, labour and maintenance. The rail system has now been replaced with an AI solution, over-delivering on the original proposal and creating a solution much more viable for wider adoption. The rover uses its onboard camera to plot its navigational route by following the crop. The AI system upgrade also necessitated mechanical and electronic changes to improve the accuracy of the steering. Both the automatic crop following and the additional front wheel steering can be seen here as the Rover successfully follows a crop of beans planted in an S-like shape. This enhanced navigation system is more reliable and it's more precise than the previous system. The AI steering enhancement is in fact more reliable than manual steering, especially during crop monitoring, due to the Rover's ability to autonomously maintain consistent speeds when recording. Whilst the Rover was unable to perform a U-turn at the end of a crop row unaided, it was able to successfully navigate any of the individual rows allocated to the navigation field test. The goal of the intra-row weeding task is to perform fully autonomous weeding of a crop row to eliminate the weeds located amongst the crop whilst leaving the crop undamaged. This task is actually a combination of the plant discrimination, weed destruction and field navigation tasks. The Rover will weed an area, then autonomously move to the next, following the crop until the complete row is weeded. The goal of the crop mapping task is to autonomously produce a map of a multi-row cultivated plot with variable plant density. Participants are asked to produce a map containing plant positions in terms of absolute coordinates such as UTM. Accuracy of plant positions is evaluated by comparing the participant map with the ground truth. Initially designed to be performed by the farmer's dashboard, the Rover is now capable of performing basic monitoring tasks using the algorithms developed for plant discrimination and AI navigation. Having imaged a row of the crop, the images are stitched together to create a single continuous image. There are a number of different methods available for image stitching which are currently being evaluated to determine the optimal stitching algorithm for consistent performance and clarity of output. In addition to participating in the competitive aspect of the metrics challenge, the competition also provided opportunities for collaboration with other teams and research groups. During the challenge, issues arose that the teams had not previously considered during the development of their machines. Two such issues were weight and size. Some competitors were not able to participate during wet weather due to the weight of their machine. Others were not able to participate due to their size relative to the crops being scanned. At approximately 140 kilograms and with a clearance of 50 centimeters in height, the Rover proved to be the ideal size and weight to continue to function in all conditions during the challenge. The Romi Rover team collaborated with Politecnico di Milano, who used the Rover as a platform to mount their sensor array when their Rover was not high enough to pass over the corn crop. This resulted in the Romi team gaining additional data using sensors not traditionally mounted on the Romi Rover, such as infrared, which may pave the way towards the study for novel ways of measuring crop health as well as type. It is hoped in future that as well as progressing the Rover towards a product aimed at microfarms, that the Rover will also be adopted as a base platform for other projects in the field of research.